Computer-aided engineering, engineering informatics, and computational fluid dynamics, a technical perspective of computer-aided engineering, CAE, or engineering informatics is a broad domain encompassing the use of computer software to aid in engineering analysis tasks. These tasks include finite element analysis, FEA, computational fluid dynamics, CFD, multibody dynamics, MBD, and optimization. CAE tools are integral in the engineering product development lifecycle, supporting design validation, simulation, and decision-making processes. With the advent of powerful computational resources and advanced numerical methods, CAE has evolved into a cornerstone technology in modern engineering disciplines including automotive, aerospace, civil, mechanical, and biomedical engineering. Historical evolution of CAE. The origins of CAE trace back to the mid-20th century, with the development of the finite element method, FEM, in the 1950s and 1960s. Initially employed for structural analysis in aerospace applications, FEM's computational advantages led to its integration into commercial software packages by the 1970s. Concurrently, advances in computational fluid dynamics, CFD, enabled the simulation of fluid flow and heat transfer phenomena. The 1980s and 1990s saw the proliferation of CAE tools as hardware became more affordable and software more user-friendly, culminating in integrated CAE suites that allowed for multi-physics simulations by the early 2000s. Fundamental principles of CFD as computer-aided engineering. Computational fluid dynamics, CFD, is a critical sub-discipline within the broader field of computer-aided engineering, CAE, concerned with the numerical analysis of fluid flows and associated phenomena. Through the solution of governing partial differential equations, CFD enables engineers and scientists to simulate the behavior of fluids in complex geometries under diverse conditions. In the context of CAE, CFD provides a virtual environment for evaluating and optimizing fluid dynamics performance, significantly reducing the need for physical prototypes and experimental testing. It plays an indispensable role in industries ranging from aerospace and automotive to biomedical and energy systems. CFD is founded on the numerical solution of the Navier-Stokes equations, which describe the conservation of mass, momentum, and energy in a fluid medium. These equations are non-linear and coupled, often requiring sophisticated discretization and solution techniques to achieve stable and accurate results. The core principles include: 1. Governing equations. O continuity equation, mass conservation. O momentum equation, Newton's second law. O energy equation, first law of thermodynamics. 2. Turbulence modeling. O direct numerical simulation, DNS. O large eddy simulation, LESS. O Reynolds average Navier-Stokes, RANS, models, including K-epsilon, K-omega, and SST. 3. Discretization methods. O finite volume method, FVM. O finite difference method, FDM. O finite element method, FEM. Each discretization method translates continuous equations into algebraic forms solvable on a computational mesh. The CFD workflow in CAE. A typical CFD analysis within a CAE framework involves multiple stages. 1. Pre-processing. This stage includes geometry creation or import, usually from CAD models, domain discretization, meshing, and specification of boundary and initial conditions. The quality of the mesh is paramount, as it affects both solution accuracy and computational efficiency. 2. Solver execution. During the solving phase, the discretized equations are computed iteratively using numerical solvers. Convergence criteria, under relaxation factors, and time-stepping schemes are crucial parameters. Depending on the problem, steady-state or transient simulations may be employed. 3. Post-processing. The final stage involves analyzing simulation results using visualization tools to extract key performance metrics such as velocity fields, pressure distribution, temperature gradients, and streamlines. Software like ParaView, TechPlot, and ANSYS Fluent's built-in tools support advanced data analysis. Industrial application. CFD has transformative impacts across various sectors. Aerospace engineering. Airflow over aircraft wings, aerodynamics. Jet engine cooling and combustion analysis. Flow-induced noise and vibration prediction. Automotive engineering. External aerodynamics and drag reduction. Internal combustion engine simulation. HVAC system performance and cabin comfort. Civil and environmental engineering. Wind load analysis on structures. Urban airflow modeling and pollution dispersion. Hydraulics of water distribution system. Biomedical engineering. Blood flow in arteries and heart valves. Drug delivery and respiratory airflow. Microfluidic device simulation. Energy and power system. Combustion dynamics in gas turbine. Heat exchanger performance. Renewable energy systems such as wind turbines and solar thermal collectors. Integration with multiphysics and optimization. Modern CAE platforms enable the coupling of CFD with other physical phenomena to facilitate multiphysics simulation. CFD structural, FSI, fluid structure interaction analyses allow for the study of deformation in response to fluid forces, e.g., aeroelasticity in wings. CFD thermal. Thermal simulations enable the evaluation of heat transfer in fluid systems, essential for electronics cooling and process engineering. CFD chemical reaction. Combustion and reactive flows require coupling with chemical kinetics for accurate modeling. Additionally, optimization algorithms, e.g., genetic algorithms, adjoint methods, and gradient-based approaches, are increasingly integrated with CFD tools to automate design exploration, enhancing product performance and efficiency. Numerical challenges and solution strategies. CFD presents several technical challenges that demand robust methodologies. 1. Turbulence modeling. The need for accurate yet computationally feasible turbulence models necessitates careful model selection based on Reynolds number and flow characteristics. 2. Mesh quality and adaptivity. Structured versus unstructured meshing, boundary layer resolution, and adaptive mesh refinement, AMR, are crucial for capturing critical flow features. 3. Convergence and stability. Numerical instabilities can arise from improper discretization or boundary condition specification. Time step selection and solver settings play a vital role in ensuring convergence. 4. High-performance computing, HPC. Large-scale CFD simulations benefit from parallel computing, requiring efficient solver scaling and memory management. Emerging trends in CFD. As computational power grows and software becomes more advanced, CFD continues to evolve in exciting directions. 1. AI and machine learning. Surrogate modeling for rapid design evaluation. Data-driven turbulence modeling. Intelligent meshing and adaptive simulation control. 2. Cloud-based simulation. Democratization of CFD tools through SaaS platforms. Scalable simulation environments for SMEs. Collaborative, real-time simulation workflows. 3. Real-time CFD and digital twins. Reduced order models enabling real-time performance prediction. Integration with IoT sensors for live model updates. Predictive maintenance and operational optimization. 4. Immersive visualization. Use of virtual reality, VR, and augmented reality, AR, to explore fluid dynamics data. Enhanced design communication and stakeholder engagement. Computational fluid dynamics stands as a cornerstone of modern computer-aided engineering, offering a powerful framework for understanding and optimizing fluid flow systems across diverse domains. Through sophisticated numerical methods and integrated CAE platforms, CFD facilitates a paradigm shift from experimental to virtual testing, accelerating innovation and reducing time to market. The continuous integration of AI, cloud computing, and real-time simulation into CFD tools promises to further expand its capabilities, making it an indispensable asset in the digital engineering toolkit. Technological foundations of CFD as computer-aided engineering, CAE. Computational Fluid Dynamics, CFD, is a vital field within computer-aided engineering, CAE, that focuses on the numerical simulation of fluid flow and heat transfer. By leveraging mathematical models, numerical algorithms, and high-performance computing, CFD empowers engineers to design and analyze systems where fluid motion is a key factor. The increasing complexity of engineering systems and the demand for optimization in performance, cost, and sustainability have made CFD an indispensable tool across multiple industries. This essay provides an in-depth exploration of the technological foundations, numerical algorithms, programming paradigms, and engineering applications of CFD within the CAE domain. CFD relies on a range of computational technologies to solve the governing equations of fluid dynamics. These include high-performance computing, HPC. HPC is crucial for solving large-scale CFD problems involving millions of degrees of freedom. Parallel computing architectures, distributed memory systems, and GPU acceleration significantly enhance the computational efficiency of CFD solvers. Mesh generation and adaptive grid. Mesh generation converts a physical geometry into a discretized computational domain. Structured, unstructured, and hybrid meshes are used depending on the complexity of the geometry and the desired resolution. Adaptive mesh refinement, AMR, techniques dynamically refine the mesh based on solution gradients, ensuring high accuracy without excessive computational cost. Visualization and post-processing tools. Advanced visualization software, e.g., ParaView, TechPlot, FieldView, facilitates the interpretation of large CFD datasets. These tools support contour plots, vector fields, streamlines, and ISO surfaces, enabling engineers to assess flow patterns, identify anomalies, and make informed decisions. Numerical algorithms in CFD. The core of any CFD simulation is the numerical solution of the Navier-Stokes equations, which govern fluid motion. These equations are typically discretized using various algorithms. Discretization techniques. Finite volume method, FVM, conserves fluxes across control volumes, widely used in commercial and open-source solvers. Finite element method, FEM, offers flexibility for complex geometries and higher-order accuracy. Finite difference method, FDM, simpler to implement, suitable for structured grids and educational use. Solution schemes. Time integration. Explicit and implicit schemes are used for transient simulations. Implicit methods allow larger time steps but are computationally intensive. Pressure-velocity coupling. Algorithms like SIMPLE, PISO, and SIMPLEC ensure mass and momentum conservation in incompressible flows. Linear solvers. Krylov subspace methods, e.g., GMRES, BICGSTAB, and multigrid techniques are employed to solve large sparse systems efficiently. Turbulence modeling. Turbulence modeling remains one of the most challenging aspects of CFD. Models include Reynolds average Navier-Stokes, RANS, K-epsilon, K-omega, and SST models are used for steady-state, time-averaged flows. Large eddy simulation, LESS, resolves large turbulent structures. Subgrid-scale models account for smaller eddies. Direct numerical simulation, DNS, solves all turbulence scales but is limited to simple flows due to extreme computational cost. Programming and software development in CFD. Modern CFD tools are developed using advanced programming languages and software engineering practices. Programming languages. C, C++. High-performance CFD solvers are typically written in C or C++ for efficiency and control over memory management. Fortran. Historically dominant in scientific computing, still used in legacy codes like NASA's Overflow or OpenFOAM modules. Python. Increasingly used for pre-processing, scripting, automation, and coupling with machine learning algorithms. Open-source frameworks. OpenFOAM, a modular C++ library providing solvers and utilities for various fluid dynamics problems. SU2, Stanford University Unstructured, developed in C++, focused on aerodynamic shape optimization. Code_Saturn and Elmer, other open-source alternatives offering robust multi-physics capabilities. Parallelization and scalability. MPI, Message Passing Interface, and OpenMP are widely used to parallelize CFD solvers. Hybrid parallelization combining CPU and GPU resources is now commonplace, especially in large-scale simulations. Engineering applications of CFD. CFD is applied extensively in engineering to model and optimize systems involving fluid flow, heat transfer, and mass transport. Aerospace engineering. Aerodynamic analysis of aircraft and spacecraft. jet propulsion and exhaust system design, thermal control in high-speed vehicles, automotive engineering, external vehicle aerodynamics for drag and lift prediction, engine combustion analysis and emission reduction, cooling system optimization for engines and batteries, civil and structural engineering, wind flow around high-rise buildings and bridges, ventilation systems in tunnels and underground facilities, urban air quality and pollutant dispersion studies, biomedical engineering, simulation of blood flow in arteries and heart chamber, airflow modeling in respiratory systems and ventilator, design of drug delivery mechanisms using microfluid energy system, thermal performance of heat exchangers and boiler, flow dynamics in nuclear reactors and cooling tower, optimization of wind and hydro turbine blades, AI and quantum technologies in CAE. The integration of artificial intelligence, AI, and quantum computing marks the next frontier in CAE advancement. Artificial intelligence in CAE. AI enhances CAE capabilities by enabling surrogate modeling. Machine learning models approximate complex simulations for faster evaluations. Automated mesh generation. Deep learning identifies optimal mesh densities and refinement zones. Predictive maintenance. Trained models forecast component failure from CAE-derived stress, strain histories. Design optimization. Reinforcement learning and genetic algorithms explore vast design spaces. Quantum computing in CAE. Quantum computing holds transformative potential for CAE through its ability to solve high-dimensional problems exponentially faster. Quantum annealing. Applied in topology optimization and complex constraint satisfaction problems. Quantum algorithms. For solving sparse linear systems, which underpin many phi and CFD problems. Hybrid quantum classical models. Combine quantum subroutines with classical solvers to reduce computation time in parameter estimation or uncertainty quantification. While still in early stages, these technologies promise to redefine the computational boundaries of engineering simulation. Integration with AI and machine learning in CFD. Recent advancements in artificial intelligence, AI, are augmenting traditional CFD methods. Surrogate modeling. Neural networks and Gaussian processes replace high-fidelity models for rapid predictions. Data-driven turbulence models. ML algorithms are trained on DNS data to improve turbulence predictions. Smart meshing. AI algorithms assist in generating optimal mesh distributions based on past simulations. Challenges and limitations. Despite its capabilities, CFD faces several limitations. High computational cost for transient and multiphysics problems. Sensitivity to boundary conditions and numerical schemes. Steep learning curve for effective software usage and interpretation of results. Validation requirements to ensure predictive accuracy. Conclusion. Computational fluid dynamics, as a core discipline of computer-aided engineering, plays a pivotal role in simulating and optimizing fluid-based systems. The combination of sophisticated numerical algorithms, powerful computing technologies, and flexible programming environments allows CFD to address complex engineering challenges with high accuracy and efficiency. As the integration with AI and cloud computing deepens, and as new solver techniques emerge, the future of CFD promises to be even more dynamic, accessible, and impactful in the engineering landscape.